All right, let's get right into it. We are surrounded by things made with just mind-blowing precision. I'm talking about our phones, car engines, you name it. But have you ever stopped to wonder how they're actually made? Well, today, we're pulling back the curtain on one of the biggest secrets in manufacturing: machining.
So how in the world do you take a raw, solid block of metal, like this, and subject it to what really looks like controlled violence? I mean, you've got a spinning tool, coolant blasting everywhere, and forces strong enough to literally carve steel.
And somehow transform all that chaos into this? A part that is so complex, so precise, with surfaces so perfect they're practically mirrors. You know, it really looks like magic, but I promise you, it's not.
The answer is a process that's this incredible mix of brute force and super high-tech strategy. It's a world where raw power has to meet microscopic precision. And right now, we're going to break down exactly how it all works.
Okay, so first things first, let's lay down the ground rules. What are we actually talking about when we say the word machining?
At its absolute core, machining is all about controlled removal. You start with a bigger piece of material than you need, and you strategically cut away everything you don't want to reveal the final shape. Honestly, think of it like a sculptor carving a statue out of a big block of marble. Same idea.
And that makes machining what we call a subtractive process. Now, this is the complete opposite of what many of us think of today, which is additive manufacturing, like 3D printing, where you're building a part up, layer by tiny layer. So to put it simply, machining carves away while 3D printing builds up.
And all this carving really boils down to a few core moves. The first one is turning. This is where the part itself is spinning like crazy and a fixed tool cuts into it. It's how you get all those perfect cylindrical shapes.
Then there's milling, which kind of flips the script. In this case, the part is held still while a spinning tool with multiple teeth moves across it. This is how you create all those complex surfaces and pockets and features.
And of course, there's the one we all recognize, drilling. It does exactly what you think it does, makes round holes. And believe it or not, those three simple actions, turning, milling, and drilling, are the fundamental building blocks for just about every machined part on the planet.
Okay, so if those are the moves, how does a machinist decide how to use them? Well, it's not guesswork. They follow a playbook, and it's built around three absolutely crucial variables.
These are called the cutting conditions. First up is speed. That's how fast the tool or the part is spinning. Next is feed, how fast the tool is traveling across the surface. And finally, depth of cut, how much material you're peeling off in a single pass. If you get these three right, you get a perfect part. Get them wrong, and, well, you get a very expensive piece of scrap metal.
But here's the catch. That playbook, it changes completely depending on what you're cutting. Just look at this table. It shows the machinability for different types of aluminum. A rating of 1 is like slicing through warm butter. A 5 means the material is fighting you every step of the way. The big takeaway here is that a machinist has to be a master of adaptation, changing their strategy for every single material they touch. And that strategy almost always breaks down into two stages. First, you've got roughing cuts. This is the brute force part. We're talking high feeds, deep cuts. Just get that material out of there as fast as humanly possible. Then, once the basic shape is there, you switch to finishing cuts. These are slow, shallow, and incredibly precise. This is all about hitting that exact dimension and getting that beautiful surface finish.
Okay, that's all well and good for aluminum, but what happens when the job is machining something like hardened steel, a material that's almost as hard as the cutting tool itself? Well, that's when you enter the big leagues.
For these super hard materials, your standard tools just won't cut it. You need specialized gear. Coated carbides are the tough workhorses. Ceramics are like Formula One cars, unbelievably fast, but super fragile. But the undisputed champion for finishing hardened steel is Cubic Boron Nitride, or CBN. It's one of the hardest substances on Earth.
But listen, just picking CBN isn't enough. It's not that simple. As this quote makes crystal clear, the specific grade of CBN you choose is absolutely critical. Some grades are built tough, for choppy cuts, while others are designed for that perfect smooth finish. And using the wrong one isn't a small oops, it's a very common and very expensive mistake.
This is where we shift from just talking about materials to modern strategy. Because to machine these tough materials well, you can't just push harder. You have to work smarter. Welcome to the world of high-speed machining.
And the absolute #1 golden rule of high-speed machining is this simple idea. Maintain a constant load on the cutting tool. It's the sudden shocks, the spikes in force, that destroy tools. So the goal isn't just about going fast, it's about being smooth and consistent.
And this visual says it all. On the left, you see a conventional toolpath. Look how it just slams into that sharp corner, creating a massive spike in force. Ouch. Now look at the right. That's a modern trochoidal toolpath. It uses these smooth, circular, peeling motions. It never buries the tool, which keeps the cutting force totally constant and manageable. That right there is the secret to both speed and tool life.
And that brings us to our final and maybe the most important point of all. The tool matters, the path matters, but what we've learned is that real success, that comes from looking at the entire system.
It is so much more than just the cut. See, the best engineers, they don't just fixate on that one single operation. No, they think about the entire system, what's known as the process chain. This analogy just nails it. Having the world's best, most expensive cutting tool, but then sticking it in a cheap, weak tool holder? That's like putting budget tires on a Formula One car. You've completely undermined the whole system, and it is guaranteed to fail.
This process chain, it includes everything. It starts before you even turn the machine on, with heat treatment, making sure the material's hardness is uniform. Then you need a rock-solid, precise tool holder. From there, you program a smart toolpath in your CAM software to keep that load constant. And only then, as the very final step, do you choose the perfect cutting tool for the job. If any single link in this chain is weak, the entire process falls apart.
So we end on this thought. Yeah, the cutting tool is where the rubber meets the road, it's where the action happens. But as we've seen, it's just the final step in a long, long chain of critical decisions. It's about a shift in thinking, from just being a machinist to being a process strategist. And that is the real secret to how we shape our modern world.